Hey, what's going on, guys? Let's look at this problem right here. Here the question is asking, silicon is doped with boron to a concentration of 4 times 10 to the power of 17 atom per centimeter cube. Ni is equal to 1.5 times 10 to the power of 10 per centimeter cube, and Kt over Q is equal to 25 millivoltage at 300 degree Kelvin compared to undoped silicon, Fermi level of doped silicon. So here the question is asking to find out the Fermi level of doped silicon compared to undoped silicon. Fermi level is what? EF, okay? And undoped silicon mean there are two types of semiconductor we can have. We can have intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor is a pure semiconductor. So when they say undoped silicon, it means this is pure. So this means this is intrinsic semiconductor. So that's going to be EI, okay? Now we have to compare the location of Fermi level with respect to EI. And also in the question they have mentioned this is doped with boron at boron impurity. It means boron is a trivalent impurity, so this is going to be acceptor. So the given concentration is for acceptor. So we can say Na, that's the acceptor concentration, that's going to be equivalent to 4 times 10 to the power of 17 atom per centimeter cube. Now we have to choose a suitable equation that is related to EI, EF and also acceptor, or in other words you can say holes, okay? Acceptor are holes. So if you look at the equations, the most suitable equation is going to be this one, that is EI minus EF, that is equal to KT ln of P naught over Ni, okay? Now KT, we have KT over Q, that's 25 millivoltage, okay? KT over Q is given, that is equal to 25 millivoltage. Now we want to find out what is KT is. KT is what? 25 millivoltage times Q. Q is nothing but the charge, but it doesn't matter whether it's hole or electron, the charge value is going to be equal. So instead of Q we can write electron, so milli electron volts, because we are going to express our final energy answer in terms of electron volts, so it's better to keep it as electron volt, okay? So instead of Q I plugged E. Now here we know the KT value already, 25. Instead of milli I put 10 to the power minus 3, and then electron volt, we are going to keep it as electron volt. And Ln, P naught is nothing but acceptor concentration, so number of acceptor added is going to be the number of holes concentration. So this is equal to, approximately equal to P naught. So we can replace P naught with this value, 4 times 10 to the power of 17. And intrinsic concentration, that's given by 1.5 times 10 to the power of 10 in the question. So we can plug that one here, 1.5 times 10 to the power of 10. Now we have all the values, and we just have to calculate this one. If you calculate this one, you are going to get 0.427 electron volt. So this is EI minus EF. And if I express intrinsic energy band with respect to EF, we are going to have 0.427 electron volts plus EF. Okay, now let's go ahead and draw this one in a diagram and see the location of this one. So here we are going to have conduction band, and also we are going to have valence band, and intrinsic band is exactly in the middle. It's always in the middle. So this is EI. Now the bottom part is the valence band, and the top part is the conduction band. Here we are dealing with acceptors, so we are going to have this one, we are going to have holes. So holes is almost near to valence band, always near to valence band, so it's going to be somewhere here. So this is going to be the Fermi level band, right? EF. The distance between this and this is given by 0.427, so electron volt. If you add EF plus this one, that's going to give you EI. That's what we derived right here. EI is equal to 0.427 electron volt plus EF. And that's how we do this kind of problems. I hope this helps. Thanks for watching.